treating that, and I kind of wasn't. Right, but in 2 dimensions, certainly it predicts transition. Okay, so I think that's all I wanted to say about the seminal paper of this field. If there's any point, yeah. Yeah, the dimensionality is, yeah, in the value of k here. Not just dimensionality, so that's the thing that I wanted to say. It's not just the dimensionality, it's the connectivity of the lattice. And, yeah.
What is the value of k when a dimension is 1?
So, right, so the point is that you're asking how many, so it's 0. Right, because there's not, you're basically asking that you start drawing all these paths. Are you getting an exponentially growing number of paths with length or a finite? And the point is that in 1 dimension you don't have this phase space to have different paths. But so let me just double check. I think that if you actually allow for even finite range hops, but more of them, you might actually have you might actually have. It may actually be powerful. It may not be. I have to check. I'm sorry, I'm blanking out.
You're referring to it's going from its initial place to the end.
Yeah.
But you can't backstep it all.
Yes, but we're at this point, at this level of theory, we're ignoring everything but non-self-intersecting paths. Yes, if you allow for doing this, all right. But I think here actually, if I didn't say this already, in getting this far to this sort of integral, we used strongly the fact that individual sites have uncorrelated disorder, and so if you only visit each site once, you never have to consider sort of correlations between the disorder potential. That's important. And it's possible to treat revisiting of the path, but that doesn't produce complications, at least at the perturbative level.
What is the self-intersecting path?
Well, it's a path that sort of goes back and forth. I mean, that's one way. I actually don't know. So in higher dimensions, the path is basically well, in 1D, so basically, you want to ask about the length of the path. If the length of the path is the distance between 2 points, and it's not self-intersecting, but it can backtrace, and a path that's sort of revisits the same point more than once, right? It can change direction. Hence the name, forward approximation. So in one, quite small. Only go where you want to go.
This approximation we are doing, this is beyond the mean field approximation, right?
What's a mean field approximation?
Because you are considering all kinds of whatever you're talking about. It's almost exactly the same.
Well, it's not. So I think the question is, so mean field approximation is, this is the first time most of us hear it, is you take, you take a statistical sum or a path integral and you find saddle points.
Right.
And so they could be a single, so a single configuration. So in that sense, if there was a dominant path, so if you were doing Feynman path integral, there was a dominant path, and you would just look at that path, right? One can call that mean field approximation. Here, one is doing interference, while one is looking for interference between different paths.
So
That's right.
I'm asking because
But it's not exact in the sense that there are all kinds of paths that are just not included. And one can, like for example, I could spend some time sort of, also in the original paper, there was a discussion of what is being ignored, and so one of the issues is that if the two, if one of these deltas is anomalously small, then of course you're going to get a particle, in perturbation theory, you'll get very large terms where the particle would just go back and forth, back and forth, back and forth between the 2 points. And those corrections you can either estimate, which was done originally, or you can actually do that to all orders. It's kind of like, it's a local resonance, and you can resum it to infinite order even. But again, then you're not including things that are much more sort of basically a resonance of 3 sides sort of doing this. The question is, where do you stop? Right, so I think any kind of a local problems in perturbation theory can be incorporated, and they can actually change the just since it's very different. Well, no, it's actually similar to conventional mean field theory, that you can include fix-ups, and that shifts your critical point. And so similarly, if you, for example, resum, one kind of sort of revisiting, you can shift the critical point maybe by 2% or 5%. It's not clear, right? If there was a mode of failure of this, like, we know about Mermin-Waldman type arguments, that you just find a generic mode of failure. Then you could figure out why this is wrong. And so in particular, already in the original paper, there was a discussion of what would really screw everything up is that if you have long-range hopping, that already at low orders it doesn't converge. You cannot have even the phase, but I think a more interesting question is that what if you can, have a well-behaved, sort of seemingly well-behaved mean field theory, but then you introduce you realize that there's a whole other class of paths that's shifted by 100%. Right, so I think that these are the kinds of things that people have worried about this on and off, but nobody has produced a clear sort of a design method for how to make these kinds of calculations not reliable. Right? So it's and people generally, I think the controlled way to study this would be to do some numerics where you vary something in your model and you vary something in this theory, and you see just how the two solutions would vary. The trouble is the numerics are not very, even nowadays numerics are not very easy to interpret, even for non-tracking problems, let alone think about it. Okay?
This is the mean field analysis, right? This is correct on the beta lattice.
That's not my definition of mean field theory, that everything that's correct on the beta lattice. But okay, yeah. If there are people who...
That tends to be where mean field approximations are exact, right?
Fair enough. No, it's just, sorry, beta lattice is something that, so beta lattice is a lattice that's a tree. And so on the tree you can write, recurrence relations, and they don't have corrections. Yes, I think I should. Yes, I think that's a helpful comment. The trouble is that the reason, but just having acknowledged the usefulness of the comment, I also want to justify my reaction that somehow you generally expect mean field theories to be almost generic. Some exponents shift from being 2 to 2.5, but somehow the nature of the phase transitions on the specifically localization phase transition, but also many other phase transitions on the beta lattice on these trees, it's very different. There's none, there are all kinds of details that we don't believe are generic to finite dimensional. So therefore, it's a different problem. Okay. All right, so let me, in the remaining 25 minutes, let me shift gears. Something much more straightforward. So you might expect that one-dimensional disordered problems would have been studied maybe already in the 19th century, because that's what electromagnetic transmission lines are, one-dimensional disordered problems. And in fact, there was a paper more or less around the time of this paper, someplace published in some radiological or radiophysics journal in Soviet Union, where one-dimensional localization was treated essentially exactly. The authors were first name Okay, I'll put that in notes. Vasiliev is the second author. But that paper has not been influential at all. It was sort of rediscovered in the 70s, memory recall. That's right. So I think also methods have evolved and interesting questions have evolved as well. So we're going to look at localization in one dimension, and we're not going to think in terms of perturbation theory at all. At least not the perturbation theory about the localized states. The idea is that we want to think of weak disorder. We want to look at histograms of, put it in quotation marks, in the sense that we can agree on what to look at once we have a good sort of a description. And just at the physical level, the localized states they look like bound states. The formalism that we're going to use here is the formalism of transmission. So we're essentially, the presence of localization is a statement that transmission through a wire, you get evanescent transmission, basically, you get attenuation. And so that's the kind of stuff that we're going to look at. And so the technology, and I honestly do not know who came up with this. It must be, again, dating back to Maxwell times, but I don't. So transfer matrices. And what's the idea? So now we're going to look at the Schrödinger equation, and we're going to look at it in sort of as a, that's what it is, the nearest neighbor hopping. And the idea is to write, okay, if you're familiar with this, I apologize, I just wanted to be very self-contained. So this equation, written as a scattering problem, looks like matrix vector type multiplication, right? So we want to think of this. Let's see, probably going to run into a problem with redundant notation. So this is a transfer matrix. You have a state on a bond connecting n and n minus 1. You connect it to a state on the next bond over. Yeah. This is Schrödinger equation. Huh? Sorry, except E doesn't have n. Yes. Yep. Correct. Thank you. Right. So there doesn't seem to be any mileage in writing this unless you're already familiar with this technology, and particularly in clean problems, say 1D Ising model, or one-dimensional step-mech problems, or quasi-one-dimensional step-mech problems. Clean problems, also step-mech. You know, the great thing about transfer matrices is that you can describe the partition function as an infinite product of transfer matrices, and if the problem is clean, you only have one problem to solve. Just to remind you, and even though transfer matrices need not have left-right symmetric eigenvectors, but in clean problems you can arrange things that way, which is always very convenient. And so you can take infinite traces by taking eigenvalues to the nth power. And if you have more eigenvalues, it just continues out, and it's a very, very powerful simplification bookkeeping. I mean, as you can see, it starts off essentially as a bookkeeping trick, and very quickly it sort of escalates to.
If you increase small,
If you increase what?
If you increase small, if you have lots of sites, it's just going to be essentially one.
Depends on the spectrum, yes. Right, so what happens in stat-mech problems is that these things are function of temperature, and they're different functions. The largest eigenvalue gives you essentially the partition function. If you now consider correlation functions, they will involve matrix elements between the eigenvectors of the transfer matrix, and so decay of correlation functions is essentially a ratio of eigenvalues. Yeah, I mean the correlation length is logarithm of inverse correlation length is logarithm of the eigenvalue ratios. So it's a very sort of a compact way, and you can see, you know, I'm more of a user of transfer matrices rather than sort of really understanding it very deeply, but you can see that there's all kinds of processes, multiple scattering processes that are just naturally coded in. So if you think, I mean, I'll get to sort of some of this, but the idea is that if you send in a left-going wave, it goes in, scatters once here, comes out, scatters once here, transmits to the first one, back scatters again, second one. All of that is just encoded in this sort of a product. And the power, of course, is to be able to look, at individual transfer matrices and learn something about this infinite product. Anyway, if you need nighttime reading, just picking up a problem that's solvable by transfer matrices is it's always a fun exercise. Right. So what do I want to say? What I want to say next is that we can look now in the disordered problem. Each of these t's will be different because of this en. So we'll look at the total transfer matrix for going from 1 to n, t to j equals, right? And what you notice is that just because the determinant of one of them is also, because of the determinant of each of them is 1, the determinant of the product is also 1. Again, it's mathematical triviality, right? Because of that, we can actually rewrite it in a pretty efficient way. So you can see that there are, by this point, there are n random numbers packaged in here, but once you've gone to this sort of a product, because of that feature, and again, if you've seen the 1D Ising model, this is starting to smell familiar. Right, we can describe the solution, the scattering solution, the complete solution, in terms of just two numbers, eta and phi, and you know, the lambda plus minus, ae plus minus. Yeah. Okay. Now, if you want to connect this to basic quantum mechanics or whatever, optical transmission, your transmission coefficient, right? So the idea is that you send in, you know, amplitude 1 wave, you know, something gets through. Oh, let me draw a picture in case you don't. Say again? Yeah, I'll address that just a second. The idea is to render them, right, good point. Well, actually, let me just say what I was going to say next, and that might. There's freedom, and I've exercised some of that freedom in writing that. That's a valid question. I should bring this down, right? Okay. So let me make a basis. So I don't like this basis. This This is written in local basis, and that would be the right thing to do if we wanted to somehow study localization, but we want to study sort of weak disorder regime in this case, and so the natural